Well, I know you don't want to admit it, but these log equations are kind of fun, aren't they? Well, we're going to dive into some more advanced bear traps today with regards to solving our log equations, but let's take a look at some of our basic fundamentals here. So there's two types of scenarios, right? There's this one scenario where there's logs on both sides, right? And so if we could say that log base b of m is equal to log base b of n, then those respective inner functions, this portion and this portion, must be equal to each other. We could say this mathematical symbol right here is the symbol for implies, and it's a really cool symbol. So the fact that this log equals this log implies that the quantity m must equal the quantity n. In other words, we just kind of chop off the logs on each side. Or the other idea is that there's only logs on one side, and then what we're going to do here is we're going to convert it into an exponential equation, and we like to use a technique called around the world. And so we'll circle our subscript here, our base, and that's kind of our cue for our starting spot. And we're going to go the long way around, and we're going to raise b to the power of c, and then set that equal to the quantity m. So it would look like this: b raised to the c equals m. So we're going to be doing one of those two maneuvers throughout all these problems. So in our first one, and this is the bear trap, it kind of at first glance feels like there's logs on both sides. But look at the 5 at the very, very end. Okay, so you have a term that is not in terms of a log. So what you want to do is you want to kind of gather all of the logarithmic terms on one side of the equation. And in this case, the one non-logarithmic term, leave it on the right-hand side. So I'm going to try to subtract this term over to the other side of the equation. So here's, maybe it'll look like this. Let's subtract this term over. Whatever I do to one side, I'll do to the other. And when we're all said and done, we've got the first log on the left-hand side minus the one that I'm attempting to move over, okay, equals that 5. So then what we could do is we could combine the two logs on the left using our quotient property. So when I condense the two logs into one log, it's going to be this quantity divided by this quantity, because that subtraction sign is going to transform itself into division. So let's say big parentheses, we've got x squared minus 4x divided by the quantity 4 minus x. All right, so we're in the same position that we were in up here. Whoops, I meant for that to be the highlighter. Okay, and we're going to convert it into an exponential. So what we're going to do is let's take our base, let's raise it to the 5th power, and then set that equal to this entire expression. So what's that going to look like? 2 raised to the 5th equals x squared minus 4x over 4 minus x. And I think we're starting to get ourselves out of the woods here a little bit. That 2 to the 5th is 32, and if you'd like, you could put it over 1. And we could cross multiply, so we'll go 32 times 4 is going to make 128. And then 32 times x, boom, 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 equals x squared minus 4x. Because we do have a quadratic, we're going to try to get all the terms on one side here. So we'll get 0 equals, we got our x squared. We're going to add that 32x over to make 28x, and then we'll subtract the 128. This is kind of a crazy one to try to factor. We're checking ourselves, trying to think of the multiples of negative 128 that add up to positive 28. So what are the multiples of negative 128 that add up to 28? Certainly we're going to get into the calculator and kind of play around trying to find some multiples of 128. The winning pair here that you'll find yourself falling in love with is positive 32 and negative 4. And so you could verify that now here with your calculator. Make sure they multiply to 128. And certainly when you add 32 and negative 4, that'll add up to 28. So when we tee this up, we'll get x equals negative 32, and we'll get x equals 4. And now comes the part of trying to check these answers, right? All right, so what I'm going to do is I'm going to try to substitute. I'm going to start with the negative 32. And initially, like I'm a little pessimistic. Like I'm like, will this negative number really check? So I'm going to try to substitute it back into the original. Okay, so I've got log base 2, and then it's x squared minus 4x. So it's going to be negative 32 squared minus 4 times negative 32. And then that's supposed to equal log base 2 of 4 minus negative 32 plus 5. Wow. Okay, got the pen working there. Now, believe it or not, when I plug this into my calculator, I'm going to get a very positive number here, which is good. And I'm going to get a very positive number here. In fact, plugging it into my calculator, everything worked. Everything on the left-hand side from here ended up equaling the same thing that I got over here. Now let's investigate what happens when we substitute the positive 4. So now I've got log base 2, again going back to the original, so it's going to be 4 squared minus 4 times 4 equals log base 2 of 4 minus 4 plus 5. And right away we got some bad news, don't we? We got some bad news. So in here, you're going to get 16 minus 16, that's 0. Or over here, you get 4 minus 4, that's 0. So we are going to reject, we need to reject x equals 4 because the log of 0 is undefined or does not exist. So my only solution is negative 32. How about that? I don't know how many times I've seen that where the negative number checks and the positive number gets rejected. This is just crazy, just crazy. Okay, this next example, as we kind of move and read through it from left to right, we'll see that all of the terms do have a log in them. So what we're going to try to do is just go ahead and I'm going to try to use the quotient rule to condense these two logs into one log. Well, log base 5 of x plus 2 divided by x. And I'm telling you what, if you've got a little swagger in your step here, I would not caution you. I don't want to hold you back. Go ahead and try to solve this one on your own, and then we'll compare and see if we got the same thing. Again, I think we're going to use the quotient rule because of that minus sign, and we'll go 2x minus 1 all over 3x minus 12. And then this idea of having logs on both sides allows us to basically cross those off and set this inner function equal to this inner function. I like to use that term inner function to describe the quantity that's inside the parentheses. That's the quantity that I'm taking the log of. And so that's what I like to refer to. Now, as I do my cross multiplication here, I've got to multiply a binomial times a binomial here. So what I'm going to do is I'm going to take my time and I'm going to write this out. So it's going to be the quantity x plus 2 multiplied by the quantity 3x minus 12. We'll have fun foiling there. And then we'll have this. So we've got x times the quantity 2x minus 1. So we're going to go ahead and start distributing or foiling. So we got 3x squared minus 12x. And we've got 6x minus 24. 2x squared minus x. Okay, so it looks like the bigger x squared term lives on the left-hand side here. So I'm going to move everybody to the left. I'm going to subtract that 2x squared over. I'm going to combine these two like terms and then add the x over. So after I accomplish all of that, it's going to be 1x squared. Let's see. I think that's going to make negative 5x. And we'll see if we can have any luck factoring here. Looks like negative 8 and positive 3 are going to work real nice. X minus 8, x plus 3. We'll tee that bear up. X equals 8, x equals negative 3. Now let's go ahead and check these answers and see what happens, eh? So let's say I go way back to the original here, and I want to substitute this positive 8. Okay, the first thing I've got is going to be log base 5, and it was originally x plus 2, so now it's 8 plus 2, minus log base 5 of just x equals log base 5 of 2x minus 1, so it'll be 2 times 8 minus 1, minus log base 5 of 3 times 8 minus 12. Okay, so let's see how this all works out. Looks like I'm going to get log base 5 of 10 minus log base 5 of 8 equals log base 5 of 15 minus log base 5 of, let's see, 24 minus 12 is going to make 12. Interesting. Again, the calculator can be very, very helpful on this one. But I'm going to go ahead and I'm just going to try to prove that it can be done by hand. Although, like I said, just keep it simple. Feel free to use your calculator. So if I combine these two here, it's log base 5 of 10 divided by 8, right? And over here, it'd be log base 5 of, so condensing those two would be 15 divided by 12. And does 10 eighths really equal 15 twelfths? And I think once you reduce them, if you reduce each fraction, you'll get 5/4 here. You'll also get 5/4 right there. So yeah, check. It does check. However, when we do the same thing with -3, I don't know if we're going to have as much luck. Let's see if I could squeeze it in here. So it'd be -3 plus 2. Hey, guess what? I don't have to go any further than that, because what do you see right here? I see a negative number when I add -3 and 2. And the log of a negative number is what? Undefined, does not exist. So we're going to reject x equals -3. And my only solution is +8. Winner, winner, chicken dinner. All right, I got one more fun problem for you here as we're trying to review and get ready for our next test. So I want you to consider this exponential function. The number of viewers, which is measured in thousands, during a Bills game can be modeled by this exponential function. V of t equals 125 times 1.12 raised to the t divided by 4 power, where t is the number of games played since the season started. What is our basic interpretation of this? Okay, first thing, let's address the 125. That's your initial amount. So we'll say there were initially 125,000 fans, or I should say viewers, for the first Bills game. We'll say for game number 1 at the beginning of the season. Okay. And the number of viewers, did it increase or decrease? The number of viewers increased at a rate. Now, why did it increase, right? Why did it increase? It's all because my base was bigger than 1, right? Now, if I subtract a 1 from that base, let's go 1.12 minus 1, and then move the decimal place twice. So it's increased at a rate of 12% every 4 games. Okay, because that exponent talks to us about the frequency, like how frequently did that 12%, kick in and occur. Okay, my next part that I want to do is how many viewers were there for game number 18? In other words, our second playoff game. 16 regular season games plus our second playoff game. So let's say V of 18. V of 18 equals 125. 1.12 raised to the 18th divided by 4. Let's check our calculators on that one. So I got about 208.1570455, and we're assuming if we're describing people that we're probably going to round that to the nearest integer. So I'm going to say about 208,000 viewers for game number 18. All right. Okay, so this is the really challenging part. What was the percent increase per game? We know it went up 12% every 4 games, but what percent was it each individual game? And it starts off with this idea that you could take the exponent t divided by 4 and rewrite that as 1/4 times t, okay? And what we're going to do is we're going to rewrite the original equation. We're going to say v of t is 125 1.12 raised to the 1/4 parenthesis raised to the t. So we're kind of separating the 1/4 and the t from each other. We're going to just plug in that 1.12 to the 1/4 into our calculator. And if I round that to, let's say, I'll just go 2 decimals to keep it super, super simple tonight. That's going to give me 125, and then in parentheses, 1.03. Let's go, let me go a couple more decimals just to make it more precise. 1.0287, okay, to the t. So now, of course, we're still increasing, but it's increasing at a rate of 2.87% each game. Remember, we took this base, and if you subtract 1 from it and then move the decimal place twice, you've got your rate.